a list of the physical quantities with no dimensions. First one you already know is the angular displacement. Then we have coefficient of friction, which is represented by letter mu. So coefficient of friction is defined as normal force N divided by the force of friction, lowercase f. So force divided by force, normal force divided by force of friction. Two forces cancel out. So wherever you are left with, it will just be a number with no dimensions. All right, let's see what's the next thing here. Then we have refractive index. Now, refractive index is a number used in optics. That is, optics is a branch of physics where you study how the light travels in different medium or different media, I should say. So this refractive index, it gives you a measure of when light goes from one medium into another medium, how much it's going to refract, how much it's going to bend, and which way it would bend. Okay. So that is refractive index, and you will study about it when you get to optics. Next one, strain. So if you take, let's say, a box and you push on it in such a way that it deforms, okay? So it becomes, let's see if I can draw anything here. So this was your box to begin with, right? Please pardon me, my drawing is extremely bad. And then you start, pushing on it something like this. So what this will do is it's going to deform the box. Let me use yellow color. Let's see if I can show you how the box will deform. So this is the side view. See here? So the box is kind of tilted, it has deformed. So that's how you will get this delta L over L. This gives you strain. It's a measure of how much it has deformed. So delta L is length, is how much the length has changed, and L at the bottom is the original length. So it's length, units of length at the top, divided by units of length. So this epsilon here, this is a dimensionless quantity. Okay. So let's move on to the next one. This is relative density. You want to find the density of one object relative to the other one. So you're dividing, you're taking the ratio of density of the substance and the density to the density of the reference. So density divided by density again cancels out. So relative density is a dimensionless quantity. What's the next thing? The next thing is relative error, also called as percent error. So it is actual minus expected divided by the expected. So it is like, for instance, if you did an experiment to measure the value of G, experiment, and you got it to be 9.23, while you know that theoretically expected value is 9.81, of course, meters per second square, Then to find the percent error or the relative error, what you'll do is you will take G expected minus G theoretical absolute value divided by G theoretical times 100. So at the top, the difference will be like, what? I'm going to make it 8.3 here just to make my life easy. So at the top, it is 0.63 meters per second square, right? Divided by 9.81 meters per second square. So meter per second square cancels out meter per second square. Whatever you're left with, that has no units. No units means no dimensions. Okay. Okay. Then we have Mach number, which is used a lot when you're talking about the jets, the flying jets. So it is really the local flow velocity, u divided by the speed of sound and medium. It really has to do with the speed of sound. Again, we're not going to get into the details of these things, but I just wanted you to have an idea of some of the things that are dimensionless. Lorentz factor. When you work on the special theory of relativity, or just the Lorentz, these are Lorentz equations, Lorentz contraction, and other things. Well, you do this in modern physics. So you will learn about this in modern physics. Very, very cool things here. And the last is, this is my favorite subject in physics, the fine structure constant. It is used in high energy physics or particle physics. Okay. So these are some of the dimensionless constants, sorry, not constants, dimensionless physical quantities. Some of these are formulae actually, but when you combine those quantities together, like here in Lorentz factor, you're combining it's 1 divided by 1 minus v squared over c squared, where v is the velocity of whatever the object is, and c is the speed of the light. So you're not going to really need much of these yet, but hopefully you have some idea of what I'm talking about. Sure, we could get into these to show that these are indeed dimensionless. At some point, I'll show you that here, for instance, this is dimensionless here, and how these different things are dimensionless. It is very easy to see these ones over here, right? I mean, same thing, quantity divided by same quantity. Dimensions are going to cancel each other out. Same thing over here. 1 minus v squared over c squared. V squared meters per second squared, c squared meters per second squared. Units canceled out. The only one that's going to be a little bit of work to show will be this one. And maybe I'll make a short video for this and post it for you guys. So from this lecture, what you should remember primarily is how to get the physical dimensions, dimensional formula, and you should know the principle of homogeneity, how it is used. Uh, you should know that it is possible to have a physical quantity with units, but no physical dimensions. And that would be angle theta, right? Angular displacement. And what else should you know? Then you should know the algebra, how the algebra is done when you're multiplying different physical dimensional formulae. Okay, these are pretty much all of it, and I'm going to use everything that I have taught you today in the subsequent lectures. So I'm making a few of those lectures where we're going to solve all kinds of problems of physical dimensional analysis. So I'm going to start out with some simpler problems, and as the lectures progress, I mean, I go from third lecture to the fourth to the fifth and so on, the level of the problems is going to go up. So don't miss out. Keep watching, keep studying, and don't just watch other people do math, physics. They will know how to do it. It's your time to learn how to do it. So you got to do it on a piece of paper, using a pencil, doing it old-fashioned way. Well, you don't want it old-fashioned way? Work on an iPad, work on a tablet. I don't care. But if you want to learn it, you have to work it. You have to take the pen, pencil, whatever you like to use, put it on paper, solve problems, get them wrong, get them right, whatever. But put your head into it, put your soul into them. That's when you're going to learn physics. And I promise you, it's a lot of fun. It can be a lot of fun. All right, y'all. Let's see you next time in the next lecture. Until then, you keep studying. Have a good one. Bye bye.